Welcome to another transport entry. Today we're going to be solving a system of 5 nodes. As you can see the information down here. However, we'll come back to that later. What we want to talk about is the conception behind this entire problem first. So the first step is going to be calculating the friction factor from the Churchill correlation. So let's start with that. So this equation demands both the Reynolds number and the relative roughness of the system. This Churchill correlation also comes with 2 equations, both A and B. Oops. So let's start with that. Using NumPy, as you can see, we've already had to help with the calculations, a obvious necessity when coming to terms with different equations. We need 2,7 there. Relative roughness. Close out those parentheses, raise it to the 16th. Making sure that looks good to me for now. Obviously, if anything comes up that involves an error, you'll probably see plenty of cuts in this video, as coding is a very tedious and oftentimes not too rewarding. So, as of right now, that looks correct. So, in order to get the friction factor, we need to return the following equation. Oops. Reynolds. Radius to power. As you can see, I'm not the savviest of typers, however, I'm sure we'll get through this somehow. What just happened there? There we go. Seems like something acted up and it didn't register some of the keystrokes, so it looks like that's a problem. It should be 12. Put some spacing here, let me see. No, everything looks fine. Want to make sure there's as little error as possible here. So this entry helps us find that frictional factor using the Churchill correlation, as I mentioned earlier. However, we will eventually need to find a way to calculate the flow rate, Q. Now, it's all nice, however, we're going to need to go into the delta head equations. So, moving on with a new line of code here to separate everything. I just mentioned that we're going to need delta head as a function. Now, this will involve the length and fittings of the pipe, as well as the diameter I mentioned earlier, and that relative roughness as well. Now, these are all going to come up later. However, D head needs one of 2 things, either to be defined by the velocity of the liquid or the flow rate of the liquid. So for this one, we're going to go with flow rate, which is represented as Q, and we're going to move on with the code here. So we define D head with these terms. If we use Q, that means we have to solve for the velocity. So for this, we obviously have to use the previous Bernoulli equations, which is where a lot of these equations are going to be derived from. Again, np for pi, very useful part, times the diameter, raised to the power of 2, not 2, all divided by 4. So that gives us our velocity, which we can then use to find the Reynolds number, which is rho times v times the diameter, all divided by u. Now here you can see we have a little bit of fundamental constants that we do not have included yet. So let's go ahead and add a few constants. So we mentioned rho as well. We're going to need mu. We'll eventually need the diameter and relative roughness. So let's go in and add these things. So gravity is typical 9.8, almost never leave, or 9.81, we'll be more specific here. Rho 1e3. Mu is basically the opposite, e to the -3. Opposite, I guess, is relative. Diameter is 0.1, as I mentioned earlier, and the relative roughness is actually the same thing as mu. Alright, we have those out of the way. So now we can go back to worrying about the Reynolds number. One thing to note here is that this flow rate, depending on what's entered here, can make V a negative number, which means that our Reynolds number in turn can be a negative number. That in itself is a problem because there really is no such thing as a negative Reynolds number. So we can easily get around this by simply using numpy to put an absolute value function around our value. So now that should solve any Reynolds problem we will have. So we can then return for our d head function this equation, which is obviously derived from it's called Bernoulli equation, where we can use that frictional equation again. Oops. Like I said, I'm not the fastest typer in the world. I'm trying to make sure everything looks correct as I'm doing it to avoid mistakes. Alright, so for delta head, we are interpreting the flow rate, a Reynolds number, and velocity as of right now. The problem with what we're returning, however, is that the sign of this function has to represent the flow rate. If you ask what do I mean by that, it's that we're inputting a flow rate into this equation, and the sign representing to that value for Q suggests a direction, which has to be evaluated and returned properly. So for this, you have to return, using numpy, the sign value related to that flow rate. And that can be represented using this sign function provided by numpy. With that being done, we can move on to this next step, which is more easily represented using, how do I explain this? Well, let's not explain it. Let's actually just go into the code and write out and see if I can explain it better that way. So we're going to start by evaluating the flow. And here's where obviously another delta head comes in. So we're going to use this. Delta head, which with an underscore to help not, let's keep this consistent. Delta head underscore representing to a value of delta head instead of a function. We don't want to call the function, we want to call the value, obviously, or else we'll be in for some trouble later. And then it will also use length, the fittings, the diameter, and the relative roughness. Doesn't seem to want to. There we go. So, why do we need this part? Well, that's because at first we inputted a flow. We don't actually know the flow rate of these pipes. We just know the values that were given. So we have to calculate that flow rate. And the best way we can do it is basically guessing. So we have to generate a guess for these numbers. And while we call it a guess, it's an educated guess at that. So we have to guess the flow rate. So QGuess. How can we do that? Actually, a lot easier said than done. We are simply going to take the Bernoulli equation, rearrange it, I don't want to say a ton, but rearrange it quite a bit, and we're going to put in a guess of 0.01 for that friction factor. While it's true we could guess that, we aren't playing with that. It's an educated guess here because we don't have the means to truly know. So with the orientation of the equation, we can write out as such. We can go. That K part. Our guess value of the frictional factor, length, diameter, 2 times G. And this should be correct. However, I may have gotten a little bit ahead of myself. That's right. So, similar problem to what we had earlier of that negative Reynolds value. I accidentally inputted the raw value of the D head underscore. We can't be having that. So, let's H. D head ABS. And we'll use that to represent the absolute value of our D head underscore. So just like last time, as you can see up here, we don't want that velocity being negative and screwing up the Reynolds value, so we just take the absolute value. Same thing goes for down here to ensure that this guess doesn't give us that negative Reynolds number and therefore we're not square rooting a negative. Obviously that would give us some huge blowback because you can't take the square root of a negative number. It just won't work. Ooh, and I have a question mark there. Just remind me what the heck am I doing? So, everything seems to be looking okay. There are side conditions to this, however. One such condition is as follows. If this value, I can't remember what we called it, ABS, is less than, we're going to make up a number here, extremely small, we will return the value 0.0. you ask yourself, why do we do this? It's because if that value is too small, how do I explain it? How to explain it? The Newton equation we will be using later, or function actually, provided by Skippy, has extreme difficulty converging. So this is just kind of a way to proactively avoid an incoming error later. I know I said I don't like coding too linearly, but I'm just trying to cover basics so we can avoid as many errors as possible moving forward. So now I need to continue on with this tidbit. So this QGuess will allow us to guess very accurately, not completely accurate, the flow rate given this d head value. And with that, we can then begin this f to 0 function. So let's define this. F to 0. So f to 0 is actually just going to use q. Now, as simple as that sounds, we are now going to use the previous d-head function inside of this function. So this will return the d-head function. I can just actually steal those. Smack it down there. However, we're going to subtract this d-head absolute value. Awesome. So it's going to return that number. However, this is just creating that margin of error, and it's going to actually give us the resulting flow rate. Using the Newton equation, or function, that we mentioned earlier. So we will use the f to 0 equation. Function, keep saying equation, but at this point I'm sure you know what I mean. And our QGuess. And of course we need to return the value. Of the resulting flow rate. Now, again, we need to represent the sign of our flow rate. So using NumPy, we need that sign moved out the head, multiplied by the resulting flow rate in order to add on the appropriate signage for the direction of this flow rate. And that concludes the setup for what we're going to explain. Essentially what we've done here is taken the Churchill correlation and frictional factors. We've used those at this point to construct an educated guess for our flow rates, as well as using the Bernoulli equation to restructure those guesses in order to set up this backbone known as delta head that explains our flow rates along these pipes. So from here on forth, we'll be using the given data, as I mentioned earlier, demonstrated down here. And using this data, we will eventually come up with the structure of our system. All right, so, two things to know. You can see that there's an obvious jump here. First off, I somehow managed to put 3 asterisks here, and obviously you can see the problem with that. That won't treat it as an exponent. It's actually a valid syntax error. Second thing to note, there was not a division sign right here either. So 2 syntax errors on the board for this code so far. However, that's the only thing to note since we left off. So, moving on from that point, I said we're now going to start working with the data that is provided for us for the system. So figuring out these flow rates and whatnot, it'd be very useful to have all this data at our fingertips. So we're going to start by basically unpacking all of this data. So we already have that the zero index is at 30 meters, and the zero index also has 200,000 pascals worth of pressure, and it's allocated obviously at node 0, and node 4, which is the other external node, is right there. So we have our external nodes labeled. We will eventually be labeling our internal nodes, but that will be set for later when we need to explain that. So let's start pulling apart all these arrays. So for the first column, we have our from nodes. Let's see here. Don't tell me my keyboard's acting up again. Okay. Want to work yet? Nope. Okay. So we have our from nodes are equal to, and we're going to take it from pipes, so we'll label it as pipes, which we'll draw it on from, and then we of course want that first indexing. I'm confusing myself with other languages all of a sudden. So one bad thing about coding is that you can always screw up and think of another language, unfortunately. And now the problem with this, these from nodes and the to nodes, which is what we're going to do here in a second, all have to be labeled as type. And these have to be integer 32, so using NP, we need integer 32. Right. Okay. Want to work yet? Why don't you want to work? Technical difficulties for some reason, of course. Okay. So, we said from nodes, so now we need to nodes, which is essentially the exact same thing. So let's actually just, don't use that keyboard. Control V. So it's basically the exact same thing, except instead of indexing the first columns, we want the second column. Because the first column is always represented as 0, so the second column is represented as 1. And as I said, this will be our two nodes. So, everything's going okay, except for my keyboard for some reason. We will also want lengths, which is in the third, which we will, but we don't want to use L because we've already used L. So we have lengths, set that equal to, and take it from pipes yet again, bracket, boop, boop, and then this will be taken from 2 or 3. Then finally, we're going to take our k values and do the same thing. Pipes, bracket, 3, which is actually 4. I'm speaking out loud. So now we've basically taken, for the set of 4 in each of our pipes, we have taken out each column representing our from nodes, to nodes, lengths, and fittings. With all that being put together, we can also do the diameter and relative roughness. So let's separate these from the original data we've unpacked and now generalizing some data. So the number of pipes can be represented as the original pipes using the shape command of 0. Yeah, and using that we can then create an array to fill that array with the diameters of each pipe. Now every single one has the same diameter, but that's not the problem we're looking for. We're just using coding etiquette here, essentially. So number pipes. You realize you can't see what I'm coding. Okay, so let's continue where I just left off, because I didn't realize you couldn't see it. What we have over here is us taking the number of pipes from the pipes array and figuring out how many are in there, creating an empty array and basically filling it with that array with the diameters. And then as well, we're basically going to repeat the same thing. I just realized. Boom. So that's the pipe diameter and pipe relative roughness. So we're going to do the same thing here. Cool. So, with that being done, we now have the original 4, as I mentioned, from 2 nodes, the length, the fittings. Now we also have the diameter and relative roughness. Everything's going smooth. So, what are we going to do next? So this is where it all comes down to. Not necessarily, but we're getting there. We want to know the flows through every pipe, right? So the idea that we're having here is that we need to have an array that stores the flows through every pipe relative to its own index. And the first way we can do that is using delta head, which we've gone about earlier, but now we need to do the setup for it. So we want to define, we already used flows, so we could use pipe flows. So pipe flows will be represented as the heads, as we mentioned previously. Do you want to work yet? Okay, seems like we're working again. I apologize for my keyboard acting up. So, as we mentioned, we want the open array. So let's set up an array for this. So flows is equal to np dot zeros number of pipes. Awesome. And then since we're dealing with arrays, we're going to need to set up a for loop of sorts. So I in the range of n pipes, which is what we're using for the original array. So we want some consistency here. Or as follows. And then we mentioned the delta head. I'm putting a space there. So delta head equal to. So we have everything set up. We're going to have to return something eventually. So the idea here is that we are arranging for a series to be solved within this. So let me finish setting this up so I can talk better. We need to know the flows for every single pipe in order to calculate the net flow rate into each node, right? So we need to first know the flow in every pipe to then generalize into a node to calculate per each node. So we need to worry about the original number of pipes, and we need to know the number of nodes for later. So for this flow rate, we're going to calculate these first. So you notice that there's this heads up here. Now, heads is not defined yet, which means we're going to have to define it. So we can call upon from a previous box, obviously. So heads is going to be represented as an open array, which is kind of just using numbers for right now. However, we first need to understand and calculate the number of nodes, as I mentioned later, for the net flow rate. So how are we going to do that? Well, we can first start by setting this up and saying that, looking back at our data, we can figure out the number of nodes easy by using numpy's max call sign and pulling from that pipes. So allow me to show you. So np.max function, parenthesis, call upon pipes. And then, you get this bracket trick that I learned about. We can call upon this column, which is the to column, which should hold the highest number of the node, which is 4 in this case. And then we have to set its type in integer, as we did for the previous call signs. So np dot int say 2. Now, since this only goes to nodes of 4, there are actually 5 nodes. 1 is just 0, so we'll need this plus 1 here at the end eventually when we use it later. So now that we know the number of nodes, we can calculate this array for heads. So we can set up an empty array for this one using number of nodes. So heads for external nodes. Did I use a capital N? Yes. Nodes, there we go. Is equal to that external pressure, which was represented as external P, yep. And then divided by rho and G, or rho and then divided by G. Plus then the Z value we had, which is just altitude, right? Hope you're following along. External nodes. Oops, and I did the wrong button there. Awesome. Okay. So there we have it. We now have heads and heads for external nodes. So this heads will basically just work as a placeholder in order to evaluate this array. So moving on, we have external nodes, but now we need to know internal nodes eventually. So we might as well set up some coding here. So internal nodes. Probably should have done this beforehand as I feel like I'm out of order. So we can use this by using the range function. So we can list from the set range of our n nodes, which we just set up a couple seconds ago, and then subtract from the set of external nodes, which will basically remove 0 and 4 from our set of nodes. And then parentheses and we're done. Ooh, were you out of sight when I was doing that? I apologize if you couldn't see that. So, what was the point of doing that? Let's go over it again. We now have an ability to differentiate the external nodes, 0 and 4, which 0 is essentially the starting node, 4 is our ending node, hence the reason of external. The internal nodes we can now differentiate from the external nodes. Everything is now put away. We are now focusing on the flows within each individual pipe. So as you can see, using my hands is not a good idea. As you can see, we've already set up this down here from earlier. We now have an empty array for this, for the range of the number of pipes we have. So we can now set the flow value for every set within the pipe. So now we're going to use the delta head. So now we have to use the heads from the to nodes and the from nodes. So using heads, as we set up earlier, we need the to nodes, represented from I because we're within the range here. You need to subtract the heads from the external nodes. Or sorry, the from nodes. And that's also represented from I within the range. I'm missing some brackets here. Match that, match that. Okay. Now the brackets. Last thing we need is another syntax error. We're trying to keep this as low error as possible. So, the flow of I. So, going all the way back to the original delta head, we have flow of delta head. We need, because we just calculated that obviously, we need the lengths. I would use a capital L, right? Yep. So lengths, I, and all these are going to have I now. K, it's capital K. With I, we will also need height underscore. The diameter, I, sorry, I wish I could type faster. We'll also need pipe underscore, so underscore, the roughness, I, and then that will be in parentheses, and now we have our flows, which we have to return as flow. Awesome. So now that we have the flows in each pipe going into the respective nodes, we can now calculate the net flow rate at each node, which is what we're going to do now. So we're going to define the node, and then node underscore net flow. So we need the flows for this one. So the net flow rate will be equal to, and we're just going to start with an empty array here, like we've always been doing, from n nodes. Now we're going to use this add function, this np.add at. We're going to add, oops, not the net q with the two nodes and the normal flows. And then we're also going to do the np.add.at the net q, the from nodes with the negative flow. Because if you're following if it's coming from, it's pulling out of that. If it's coming in, it's flowing in. So in is positive, out is negative. So that's why we need that negative there to explain direction. And we will return this as the net q. So what we've done in this part, we've basically explained, and I'm going to do the check this time on screen. We've explained the flows in each pipe and put a number behind that. And then we've gone to each node that pipe is attached to, and we have gone through and we have now added in the flow rate of that summation. So the flows are obviously positive or negative to influence that direction of fluid coming in or out. So let's do this check real quick. We have an error. Where's the error? End pipe is not defined. End pipe is not defined. Ah, because I didn't put the S there, right? Now delta head's a problem. I have too many brackets in there? I do have too many brackets. Okay. And that's why you check. So everything seems to be running well. So we are going to resume. All right. So the next part is still going to concern this net Q. Okay, so let's finish this code up. So what we've done, of course, the flows in all the pipes and the flow rate coming in and out of all the nodes, and then the net flow rates of each node. So from here, what's next is to do the specific flow rate for the internal nodes. So let's set this up. Net Q for internal nodes. And we're going to do this through internal pressure. So, much like we did for external nodes, you can see up here at code 33, heads for external nodes. We're basically going to do the exact same thing, but for internal nodes. So let's set this up. This for internal nodes is equal to the internal pressure divided by rho divided by G plus the altitude of the internal pressure. And then this should return we'll call it the what should we call this? C for calculated net Q. Student underscore calcs. Help if I clicked Q. Let's call it that. And then you'll have to call on the flow. Can't seem to type. Flows for the heads. Using the internal nodes. Boom. So what this is going to help us do is this is the specified net flow rate for the internal nodes. So anything that's not node 0 or node 4, that's what this is representing. So from here on out, we're going to eventually calculate the roots for because the whole idea is to get to the flow rate of the pipe, right? So we need to solve for these pressures. Because you'll notice that I mentioned that the internal P, there's no array associated with that. It truly just doesn't exist right now. And it's because it's not defined. In fact, I'm pretty sure. I don't know, it's fine with it. So we don't have internal P. Last time I remember. We have external P, but we do not have internal P. So this entire process here is eventually going to be used in this following process. So let's elaborate. We're going to need, just like we did an initial guess for Q, we're going to need an initial guess for P. So it's reasonable to say that the internal heads are the average of the known external heads. So for that, we can use the mean, so we can write it like this. Internal whatever, just internal head guess is equal to NP mean of the heads external. Note. Then, using H is equal to pressure over rho G plus Z, we can calculate P from the internal H guesses. So what that means is we can write this, if I can spell, the internal pressure guess, if I can spell, is equal to the previous equation, the internal head guess, subtracted from the altitude of the internal heads. And then that is, of course, multiplied by rho, if I can spell today, and G. So with those two put together, we can continue on to the results. So let's just say final equal to, and then we're going to use that root function that we called on earlier to basically zero out everything we need. So we want to call upon that net Q internal. Right there. And we also need then the guess. So what this is going to do, it's going to continue to iterate until everything basically becomes zero. And the idea behind this is that it should give us the flows we need given just a few more extra steps. So now we need to know the flows for each pipe. So let's calculate the flows. Is equal to calc of the heads from earlier. And then we need to do the range again. And the range of end pipes. Make sure you can see this. Probably not doing a great job of making sure you can see this because I'm just going through it. But we will do our best. Okay. Trying to see if I can move this out of the way, but oh well. So, now we almost have everything we need. So let's see how this goes. So we want to call on our from and we want to call on the appropriate values. So we need to call on from the pipes from I to 0. Close that out. To the integer from pipes of I to 1. Close that out. Want the flow, which is our answer, calculated how should it go? Oops. So we want our flow. Where is it I'm trying to call? Okay, I'm not trying to call, it's just calculate those. Calculated flows of I. And of course we need to end this. It's double, I already double. So, in theory this should spit out our answer. Net Q and term not found. Net Q and term not found. Okay. Okay, so that was one heck of a snafu, but we're back and we're done. So, as you saw where we left off, I had a very unpleasurable time figuring out what I did wrong. If you actually go back, you'll see that I messed up not only capitalization, but right here on the end there was a ED that wasn't, this one had the ED, this one didn't. I think I sat there for like a good 30 minutes figuring that out, but yes, as you can see, the entire code is now complete, and of course I'll show you here. You run it all, you get from what node to what node, representing a pipe, and the flow in that pipe relative. And you can notice that they're all positive because having started at such a high elevation, having such a great pressure, that has no problem pushing down through all the pipes to flow out from 0 to 4. So everything checks out, and I did, before I started this video, check these numbers with the supposed correct answers. So it seems that we have completed this step. So hopefully along the way everything made sense, but this has been the coding for calculating the flow rates between each pipe in this 5-node system.